Alright guys, turn to 4.4 please. And I'm going to need your cooperation since it's kind of a long lesson. You'll see why in a little bit. So here we go. So I got your 4/4 notes. So
Hey.
here's the goal for today. I know some of you have already seen the shortcut methods for graphing a line. I know that. But yes, that's pretty cool. But when it comes to graphing a line, we're going to learn how to do that with an XY table, because then you can use that XY table for any function I do. So we're going to move into some nonlinear ones, start with linear ones. Most of our graphs will be of the continuous type. Continuous means unbroken. A graph that's unbroken like this. Guys, we're a little slow about getting going. Should have packets out. Right now, just do that right now.
Why did this say okay?
Because when I drew that blue curve, I didn't pick up my pencil at all. I picked it up to start the curve, and then I picked it up when I finished, but nothing in between. So a continuous graph is unbroken. Discrete is a graph composed of isolated dots like this. Okay, that's a discrete graph. I'm drawing pictures of each type. And then the solutions are the set of all points on the graph.
Oh, yeah.
Hey guys, we need to move back to science. Let's move back to science.
Bye, Connie.
I love you.
Bye, tears.
Yeah, I know.
Alright, so here's what we're going to be doing. You guys will be creating an XY table. We call them sometimes T tables. You will be coming up with the numbers for X to plug in. Okay, is that clear? I'll say it one more time here, guys. You will be coming up with the numbers to plug in for X. If it's a real life scenario, you want to plug in numbers that are maybe just positive most of the time. If it's just try to figure out what the graph looks like, you probably want maybe one or two negative numbers, 0 and a couple positives. What I'm going to suggest on this one, if you could just fill this in, is we're going to plug in -1, 0, 1, and 2. Those are the numbers we're going to plug in. And we're going to use those numbers to get Y. As you're going through and doing the classwork and homework, all that I really need you to have is a table that looks like that, X and Y. I'm going to assume that you're going to use your calculator or mentally just do the arithmetic to get the Y. I think you can do that. I'm going to demonstrate how we get the Y on these problems. Okay. For this first one, I'm going to take and plug in -1 for X. And then we get the y, which is, in this case, negative 2 times negative 1 is 2 plus 1 gives me 3. And then I go to the next one. Negative 2 times 0 plus 1 gives me 1. And then the next one, y equals negative 2 times 1 plus 1, which is
3.
actually negative 2 plus 1. That's a negative 1. Sometimes you'll start to see a pattern. If you know it's linear and you see it's going down by 2 each time, you can skip the arithmetic and just write the next number in the pattern. Okay. So if you know it's linear, as soon as you see that pattern, you can go with it. Then we're going to take, so what you're on your classwork and homework, you would just have a list of x values, which you pick. Okay? If you're, when you guys ask me, what do I put for the x's? I'm just going to say, go back to problem 1 and do the same thing we did here. And then you're going to calculate what the y values are. And then we put those together to create the coordinates, the xy coordinates. So the coordinates in this case would be this list right here, negative 1, 3. And we plot negative 1, 3. 0, 1 is the next coordinate. We plot that point. 0, 1's right here. And then 1, negative 1 is here. And then 2, negative 3 is here. And most of our graphs will be continuous. So you can just draw a line through these. Any of these ones where I actually just make a table and draw the graph.
Yucky.
I got Kleenex on both sides of the room if you need it.
Yeah,
Landon in his hair. All right.
No, you won't.
So, okay, guys. The next one has a fraction in it. When there's a fraction in it, you might not want to use negative 1, 0, 1, and 2. A wise choice here would be multiples of 2. So here's what I'm suggesting we use for this one. Is maybe use negative 2, 0, 2, and 4. So it would look like this. So write down negative 2, 0, 2, and 4. And I'm using multiples of 2 because when I take half of a multiple of 2, I get a whole number. So it's 1/2 of negative 2 minus 1. What's 1/2 of negative 2? Negative 1. Negative 1 minus 1 is negative 2. Then I plug in 0. Half of 0 is 0. 0 minus 1 is negative 1. Plug in 2 next. Half of 2 is 1. 1 minus 1 is 0. I'm starting to see a pattern here. Negative 2, negative 1, 0, and 1 is the next one. So the coordinates, if you were to write coordinates for them, look like that. There's a whole set of coordinates. You guys don't need to list them as coordinates. You can go straight from the XY table to plot them. But we have the coordinates negative 2, negative 2, 0, negative 1, 2, 0, and 4, 1. So I graph negative 2, negative 2, 0, 1, 2, 0 is here, and then 4, 1 is here, and draw a line through it. So in the classwork, the first two functions are just like these in the classroom. Okay, they're both lines. You can do this.
Yes.
It's a little tedious. That's why the notes take so long too, but you can do it. I'm not making you do all the classwork today. I'm just selected problems. All right. When we move to real life sorts of problems, like on this one, it says the function rule W equals 146C plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries C cubic feet of concrete. So there's a number up here that represents the weight of the truck alone. Do you see what it is? 30,000 is the weight of the truck alone. Yep. If the capacity of the truck is 200 cubic feet, what is a reasonable graph of the function rule? So we're only going to do 3 points here. If the capacity is 200, you probably want to have 200 somewhere in your table. You also want to have 0 in your table, right? That's, what it weighs without any concrete in it. And then something in between. I chose 100. Some students might say, hey, why not choose 125, halfway in between those two? It's your choice. But 3 values you might choose are 0, 100, and 200. And then we plug it in here. Okay. So as we plug it in, it would look like this. W equals 146 times 0 plus 30,000, which just equals 30,000. And then the next one would be W equals 146, and then in parentheses this time I'm going to put 100 plus 30,000, which is 44,600. Yeah. And then the last one is W equals 146 times 200. Oh yeah, they didn't choose 125. It makes sense to use 100. It's halfway in between. I was thinking of the other problem. So 146 times 200 plus 30,000 ends up being, what do you get? I don't know. 59,200. 59,200. So here's the deal. If you were, you're creating an Excel spreadsheet, you're creating graphs for a presentation, business presentation or something, you get to make up what the axes look like. Like you decide what are the units on the X and Y axis, how is it scaled. You want to scale it in such a way that it's kind of a nice spread out linear function using the whole graph. If I wanted to use the whole graph for the bottom here, you count 1, 2, 3, 4, 5, 6, 7, 8. There's 9 of these. Let's see. 9 of these little tick marks. If we start at 0, there's 8 spaces in here. So if I take the 200 and I divide it by 8, I get 25. That's probably a good increment to put on the bottom, is go by 25. Remember the C represents cubic feet. So we have cubic feet down here. And if I go by 25s, that would be a 50, a 100, a 150, and then the very edge of the horizontal axis there would be 200. So I'm going up by 25s. I'm just labeling every other one, going up by 50s. So then when I plot the 3 points that I plot up here, they're kind of spread out nicely on the graph. I need to think a little bit more about it over here. If I have weight in, say, thousands of pounds along the side here, I could take 60,000 approximately and divide by 1, 2, 3, 4, 5, 6 perhaps would be a good plan there. So if I take 60,000, which is pretty close to the weight capacity, and divide by 6, I get 10,000. And so I'm going to go up by tens here because I labeled this y-axis as thousands of pounds. So 10,000, 20,000, 30,000, 40,000, 50,000, 60,000. So you're going to have to decide how to label the axes as you go through these problems. There's problem number 4 is like this in the classwork, and there's one like this in the homework as well. So the first point is 0, 30,000. It's right there. Next one is 100 over and about 45,000, so about halfway between the 40 and the 50. And the next one is 200, almost 60,000, so about right there. I could draw a line through there. And that's a graph to represent that real world function rule. Just connect those dots after you plot the points and you got it. Alright, the function rule W equals 8g plus 700 represents the total weight in pounds of a spa that contains g gallons of water. What is a reasonable graph of the function rule given the total capacity of the spa is 250 gallons? So the gallons are the outputs. Actually, the weight is the output. Sorry, weight. It's the W, weight in pounds. And the gallons is along the x-axis, that's the G. So if the capacity of the spa is 250 gallons, you could start at 0, end at 250, maybe use the 125, which is halfway in between. You know, how much would it weigh if you had it half full? And then we go ahead and plug in these values for G. So W equals 8 times 0 plus 700 equals 700. W equals 8 times 125 plus 700, which equals 1,700. And then W equals 8 times 250 plus 700, which is
2,700.
So if I think about the scale here along the bottom, it goes up to 250. I think this time there are 10 spaces. This graph is just slightly bigger than the last one. And so I could also scale it by 25. So here I have 25, 50, 75, 100, 150. So every other one is going up by 50s. And the weight in pounds, to think about this a little bit more. Looks like we have 1, 2, 3, 4, 5, 6 spaces. If I take 2,700, which is the upper capacity, and divide it by 6, I get 450. So I could go up by 450s. So 450, 900, 1350, 1800, 2250, and 2,700 up here. So think about the scale, label it, and then plot those 3 points. So I have 0, 700, which would be about here, and I just have to go approximately 0, 700, 125, and 1,700 would be up about here, and then 250, 2,700. Right up here, and then connect the dots, and you've got your line. Okay, the next problem is going to highlight the difference between a continuous and a discrete scenario. So it says a local cheesemaker is making cheddar cheese to sell at a farmer's market. So if I call this X and this Y over here, here's what it says. 1 gallon of milk makes 16 ounces of cheese. Let's stop right there. If I start at 0, I get 0 cheese. 1 gallon of milk would give me 16 ounces of cheese. 2 gallons, 32. 3 gallons, 48. 4 gallons, 64. And 5 gallons, 80 ounces of cheese. So we have an equation that would represent this. It looks like it would be y equals 16x. Okay, we're going up by 16 each time. I start at 0. Now, this scenario we have, if you vary the amount of milk, you could actually use 1.5 gallons of milk. You'd land somewhere between 16 and 32 ounces of cheese. In other words, you could use any amount of milk here and get any amount of cheese to the nearest ounce, if you will. We would call this a continuous function. So we'll label this continuous. And then we're going to graph it, starting at 0, 0, going to 1, 16, 2, 32, 3, 48, 4, 64, and 5, 80. And then connect those dots because it makes sense this is a continuous function. And very good job of that, but connect those dots. So that's an example of a continuous function. But we're going to change up the scenario for the way in which he sells it. We're going to say he's going to package this in wheels. Wheels of cheese, and they're $9 each. If he doesn't sell any wheels, he gets $0. One wheel gives him $9. 2 wheels, $18. 3 wheels, $27. 4 wheels, $36. And 5 wheels, $45. Now he can't take and cut the wheels in half or quarters or anything like that. So you can only sell whole values of wheels. That makes this a discrete graph scenario. Okay, this is a discrete graph. It's 0, 0, 1, 9, 218, 327, 436, and 545. And in this case, I'm not going to connect the dots. It doesn't make sense because I've just told you you can't sell a half of a wheel of cheese. If he cuts it in half, packaging is opened, it's going to go bad really quickly. So we'll just pretend you can only sell whole wheels of cheese. Israelite. So there are certain things like if you're buying tickets to that would be Supercross or whatever. Supercross starting in January. You can only buy certain like if tickets for certain seating, you have some combination of that. There's only certain values you can get. You can't get every combination, so you just have dots on the graph representing the different costs based on how many tickets you buy for which section. So here are a couple errors. See if you can decide here which one's continuous, which one is discrete. It says the amount of water in a wading pool in gallons depends on the amount of time in minutes that the wading pool has been filling, represented by the function W equals 3t. In this case, I would have t and w instead of x and y. And if t is 0, it's at 0. If t is 1, it's at 3. If t is 2, it's at 6. 3, it's at 9. So as you're filling a pool, does that sound like a continuous function or one that is discrete? Could you have any amount of water in the pool at any given time?
Yes.
Yeah, you could. You could have, at time 1.3, minutes, you have a certain amount in there that's different than what you have at 1.4 minutes.
Oh, yeah.
Okay, so 0, 0, we have 1, 3 here. So 1, I better scale this differently here. Probably could scale these by 1. And these by 3s maybe. 3, 6, 9, 12, 15. So 0, 0, 1, 3, 2, 6, 3, 9. And it makes sense to draw in the line. You could keep going before 12, 5, 15. Whereas over here, you're buying baseball tickets in dollars, and it depends on the number of tickets bought. So you have T versus C. If you don't buy any tickets, it costs you $0. 1 ticket is 16. 2 tickets is 32. 3 tickets is 48. So this one is discrete. You can only have those specific values for the cost. This one's continuous. So I have 0, 0 down here. We better label this. We've got 1, 2, 3, 4, 5, 6 along here. And this could go up maybe by 16, 16, 32, 48, 64. So 116, 232, 348, 464, and we'll stop there. That one's a discrete one. So continuous versus discrete, you'll be asked to tell the difference between those two. Now, not every function is linear. We've only seen linear ones up to this point. They're not all linear. Okay, there's some that'll vary, and that's when it's really important you understand this method for graphing. There are shortcuts for graphing linear ones. You may know of them already. Okay, you can find x and y intercepts. You may have heard of that or done that before. So only 2 points is all you need for graphing a line. Perhaps slope and y-intercept would work. So it doesn't work on these. So nonlinear functions. This one has a parent graph that looks like a V. In other words, all of these ones with absolute value in it will have some kind of a V pattern. If you don't see it starting to make a V, you may need to try more points in your x, y table. I would start with a couple negatives, 0, and a couple positives. That would be a good start. So -2, -1, 0, 1, and 2. Write that into your table, please. -2, -1, 0, 1, and 2. That's a good start. It's not always going to give you enough points to get a good picture of the graph. It depends on where it's translated onto the graphing grid here. So y equals absolute value of -2 minus 4. Absolute value of -2 is 2. 2 minus 4 is -2. And then I plug in -1 and do the same thing. Absolute value of -1 is 1. 1 minus 4 is, yep. And then y equals absolute value of 0 minus 4, which is -4. And then y equals absolute value of 1 minus 4, which equals -3. Notice it's coming back up. It goes -2, -3, -4. Now it's at -3. What's the next one going to be here? -2. So for this particular graph, -2, -1, 0, 1, and 2 is going to be sufficient. You'll see it makes a V shape. So -2, -2. -1, -3, 0, -4, 1, -3, 2, -2. Connect the dots. So just be aware that absolute value gives you a shape like this. If you're only doing enough points to see 1/2 of it, it'll look like it's a line. Okay? Absolute value, it's not going to be just a line. It will come up and back up eventually. So keep plugging in points until you can see that. It's one of the nonlinear ones you'll end up graphing. I'm going to throw an x cubed at you. Do you guys know how to do cubed on your calculator? There's a way to do powers of 3. If you look on your calculator on the far left, there's a little button here. It looks like this. You can type it in like this.
Not x squared.
Well, there is an x squared on there, but if you want to do cubed, you can just type in this button.
No, but in the problem.
It is, but I'm saying that you will run into a cubic in your class work. So you're going to be dealing with some powers as well. And the cubic is the one that I'm not doing in the notes, but I'm going to let you go for it and see if you can figure out what it looks like. Because theoretically, if you plot enough points, you can get a pretty good picture of what these functions look like, even if they're nonlinear.
Isn't the square the one that makes the problem?
It does. So if you could draw in here a little U shape. This is what we expect when we see an x squared. Okay, this is something of this form. So once again, I'm going to choose -2, -1, 0, 1, and 2. And then we are going to plug in those values in parentheses to that equation. So the first one will be y equals -2 squared plus 1. And -2 squared is a positive 4. So 4 plus 1 is 5. And you can use your calculator. If you use your calculator, be sure to put it in parentheses, or it will give you a -4 instead of a positive 4. -1 squared is 1, plus 1 is 2. A 0 squared plus 1 is 1. And then 1 squared plus 1 is 2, and 2 squared, 4 plus 1 is 5. So kind of similar to the V up there. I start at -2, 5, come down to -1, 2, 0, 1, and then it starts back up again. 1, 2, 2, 5. Draw in your curve. There it is. So similar, doesn't come to a point. And then, like I said, there's a cubic on there as well, and you'll have to figure out how to do that. Cube just means multiply it by itself 3 times. So when you're dealing with numbers like 2 cubed, it's just 2 times 2 times 2, which is 8. It's not hard to do in your head. All right, on your section summary, you might want to write something along the lines of, you know, if I were to summarize this, we're using tables, plugging in values. So using tables to graph functions, and that'll work. You just got to be able to plug in enough points to get an idea of what it looks like. So it'll work even for strange functions you've never seen before. That's why we teach you this in Algebra 1. So you can investigate functions no matter what, even if you don't have any idea what they look like. If you can just do the arithmetic to plug in an input, get an output, and plot the points, you're good to go.